Alright, this is another periodic trend video. This periodic trend that we're going to talk about today is the atomic radius, or you may also just hear it referred to as size of atoms or atomic size. Okay. Now, there's a couple different reasons for the trend, and we'll go ahead and show the trend first. Okay. Your atomic radius is going to increase as you go down a family or down a group or down a column, and it's going to increase as you go across a period from right to left. Okay? So atomic radius is going to increase as you go down a column, and it's going to increase as you go from right to left on the periodic table. Okay? Now the reason why we're going we're increasing as we go down is because of the number of energy levels. Okay, so we're looking at the Bohr model. Let's go ahead and take a look at two examples. Let's look at, let's go ahead and look at, say, hydrogen and lithium, just to make things easy. So here's hydrogen, here's lithium. All right. So in hydrogen, I have a nucleus. We're going to go ahead and make that nucleus red. And then for the lithium, we're going to go ahead and make that nucleus red as well. Now, if you look at the periodic table, you should be able to determine that hydrogen only has one electron if it's a neutral atom. So here's my one energy level, and look, there's my electron right there. Well, the distance from the nucleus to the outermost energy level, okay, that outermost energy level is known as a valence shell, or we call them the electrons that are in that shell valence electrons. Okay, but the distance from the nucleus to the outermost valence is going to be the atomic radius. Now, if we look at hydrogen, and then let's go ahead and we'll do lithium here. Okay, lithium has another energy level because it's another period down. It's another row down. Okay, so as we're gaining rows, we're gaining energy levels. And hopefully we see, okay, I'm going to go ahead and put my electron here. There's two electrons here, and then there's one more electron out here. Okay, so as I go down a group, the distance from the nucleus to the outermost valence electron is going to increase. Okay, so as we go down, there's going to be, as I'm going down a group, I'm going to end up with more and more and more and more energy levels, more and more energy shells. Okay, and as that happens, this is going to get bigger and bigger and bigger. So that's why as I go down, okay, as I go down, this one only had one energy level. Oops, let's go ahead and change that color. We only had one energy level right here for hydrogen. Well, in lithium, we had two. In sodium, we would have three. In potassium, we would have four. Rubidium, we would have five. Okay, and as we go, more energy levels we have, the farther the distance is from the nucleus, which is going to cause a larger atomic radius. And that's why the atom itself of, say, rubidium is larger than that of lithium. Okay? Now, the other trend that we're going to look at, no, not trend, but reason for the atomic size trend is going to be as we go across a period, okay, it's going to increase as we go from right to left. And so let's go ahead and draw a couple elements that are in the same period. Let's go ahead and say fluorine and carbon. So here are your two atoms. I know the carbon is exaggerated, but it's meant to be because it's supposed to show that as you go from right to left, it's going to increase. Okay, now I know I drew the fluorine on the wrong side, so let's go ahead and flip those around real quick. Here we go, that's better. So, if we look at the electrons that are in fluorine, there's 2 electrons here, there's 1 electron there, and then it also has 7 other ones. 1, 2, 3, 4, 5, 6, 7. Now I have them just paired up like that. They're not literally right next to each other like that. It's just easier to count. And then carbon, 1, 2, 1, 2, 3, 4. Okay, so I have 4 here, and I have 7 in that valence, and I have 4 in this one. So I have 4 valence electrons here. I have 7 valence electrons there. Now, if I look, remember, the nucleus contains a lot of positive charges. Okay? Well, as it turns out, the more positive charges that I have inside a nucleus, the more it's going to pull on these outer valence electrons. Okay? And the more valence electrons I have are going to pull on the nucleus. Okay, vice versa. They're like each other. They're opposites. So because I have 1, 2, 3, 4, 5, 6, 7 valence electrons here, they're being pulled in a lot stronger than, say, the carbon's outer electrons here. Okay? Now, as my shell itself gets, because you've noticed they're in the same period, so their shells aren't, there's the same number of shells. It's not like as you're going down a group, okay? But the number of shells are the same, but because there's more electrons in this outer level for fluorine than there is for carbon, that means that the electrons are going to be pulled in toward the nucleus more, and there's more protons in the nucleus to pull on those electrons. Okay, so more protons in the nucleus within a within a period. The more protons within a period, the stronger they're going to pull on those valence electrons, which means the smaller the atom.